Thanks for everybody coming in tonight, everybody. Appreciate it. My name is Fritz Klassen. I'm with the Office of Maunakea Management. And tonight, Dr. Mark Chun is the Associate Director for the Institute of Astronomy at ELO. And with that, he's been here for more years than I know, so I won't try and answer. 20 years? Okay. His office is right down the hall, and if I need anything, I know how to find him. So with that, I'm going to turn this over to Mark for the evening, and thank you all again for coming.
Good evening, everyone. So my name is Mark Chun. I'm an astronomer at FA. I work on instrumentation for big telescopes, specifically this type of instrument called adaptive optics, which takes out the atmospheric blurring and gives us clearer views of the sky. One of the things I get to do in this job is, because I work in that field, is go around to different sites and talk to people who have other telescope sites and compare and understand what makes a good telescope site. So I'm going to share with you some of those properties that make a telescope site good, and then why Maunakea is the best in those ways. I'm going to step back a little bit first and talk to you about something that's very special to all astronomers, and it's light. So light is, of course, the most important thing we have to understand what's going on in the universe. We don't have a way to listen to what's going on in the universe. We don't have a way to touch what's out in the universe, but we can see what's going on in the universe. So actually, at another side, we actually do have now a way to our sense of touch. It's just been developed. So you may have heard about recent discovery or recent detection of gravitational waves. So that is a way for us to understand and feel the vibrations of things that happen far away from us. And so we've developed a new sense of touch. But that's a very recent discovery. And with that, we're going to discover many things that we can't see with our eyes or with our telescopes. So open up another view of the universe. But today I'm going to talk about the sense of sight. So with light. So light is the most important thing to an astronomer, and it will be for a long time. It's the most important tool we have. So I'm going to go into a little bit of a discussion on what we can learn from light, because that's essentially what we do. And if you have any questions as I go, just feel free to raise your hand, shout out, and I'll stop and I'll answer questions. If I'm not looking at you and I'm looking down here, just shout. Okay, so light is really a messenger. It tells a story. An element of light is something we call a photon, and each photon originates someplace in the universe, in a process of physical environment. And the information about where it originates from, how it was born, is carried with it as it travels across the universe. Not only that, it imprinted on the light is information about what happened to it as it pass through the universe on its way to us. So this is the story that we're trying to understand. Each photon tells part of the story, and collectively light gives us that information. And our job is to decipher what the message is. So an example, and I find this one of the amazing things about physics and astronomy, is that a photon of light can originate a million light years away from us, a million years for it to get the light from the object to us. It can originate from a group of hydrogen atoms. And when the hydrogen atom is heated to a certain temperature, when the electron in that atom falls from a higher energy level to a lower energy level, it emits light. And that light has a characteristic color. And that photon will spread out in all directions, and some of those photons will be absorbed by other hydrogen atoms along the line of sight. They don't get to us. Some will hit a piece of dust, or a piece of soot in the atmosphere, in the universe, and it won't get to us. But some of those photons are aimed right at us, and it's just a coincidence. And they go towards us, and maybe along the line of sight, they hit a piece of something, and they get blocked. But a few of those photons get to Earth, and they hit the Earth's atmosphere, they hit the Earth's ground, and they're absorbed. Gone. That information is lost. That story is lost. But when we look with the telescopes, we collect the light. We collect those photons. And our job as an astronomer to collect it and understand what the light's saying. And deciphering that story is the job of what an observational astronomer does in a nutshell. So the telescopes are obviously a very important part of that our ability to decipher the story and make sense of what the light is doing and telling us. So tonight's talk is really about what we can tell from light, and then how the sight that we put the telescope on affects our ability to decipher the story. Okay, so this is an image of a star field. I don't know, I just randomly picked the star field. I don't know what it is. I don't know what telescope that took it. But what are some of the things we can infer from this image right away, just by looking at it? Anybody?
Lots of stars.
There are lots of stars. So this, I haven't taken an image that had a lot of stars, so that would be kind of boring. But there are all fields that have a lot of stars, but a lot of times people really deep, you see stars, a lot of stars. What about the stars are different? Colors. So we see some that are blue, some that are red. The colors don't come up very well in the picture, but they're different colors. What else?
Some are bigger.
Some appear bigger on the
Different sides.
Yeah, so some appear bigger on our image. That's an artifact of how we detect it, but indeed some stars are bigger than others. What else is there?
Artifacts. There
are artifacts from how we measure it. These crosses, stars don't have crosses, unless depending on how you draw them. But in real life, stars don't have crosses on them, but that's an artifact of how we measure it, so you need to understand that. What else?
I think we can assume that the intensities are different.
The intensity, so they have different brightnesses. So they have, stars are different. You can see that immediately just by looking at an image of a star field. So let's go through some of these things. And so somebody mentioned brightness. If we knew that all the stars were the same distance from us, and they're all the same, they're all the same distance from us, and when they had different brightnesses, then we could say there's a distribution of stars that have this brightness that are very bright, some that are not very bright. When you look at that image, what's the most common brightness star? Are they bright or faint?
Not bright.
Not bright. There's a lot of really faint stars in there. So we know automatically, just by looking at this one picture, that in this area of the sky, most stars are faint. Bright stars are uncommon. Okay, so we're learning something. Let's keep going. The other thing we can do is we can compare the stars that we see out there to our own star, the sun. And we can ask the question, how common is a sun-like star in our local universe, or in this particular place we're looking? And that gives us a sense of our place in the universe. Okay, so now let's say that from that image, we pick out all the stars that we know of the same color, let's say, and assume they're not the same distance. In that case, we can determine the relative distance by seeing how bright they are. The relative brightness of them changes. The further away you put something, the fainter it goes, the fainter it is. So we can infer distance. So now not only do we have an understanding of what type of stars are around us, we can also infer where they are with respect to us. So we have a distribution of stars in our neighborhood and what kind of stars they are. The further they are from us, the fainter they appear. So we can infer that. So sort of as a side, a couple people mentioned sizes of stars. So it's an artifact on the image that when it's a brighter star, it appears brighter in our bigger in our image. That's just an artifact how we collect it and how we display it on the screen. But in fact, there are a handful of stars we can actually measure their sizes. Most stars, although the sun is very big, stars are very big, they're so far away that their angular size is too small for us to resolve. It's like if you looked at a headlight and you're driving home. When a car's coming towards you in the distance, you can't resolve the two headlights on the front of the car because it's too far away. But as the car comes closer to you, you can see, yes, it's two headlights. That ability to resolve the two headlights, to distinguish that object, two headlights, depends how far away it is. And the size of the star, because they're so far away, you can't resolve them, except for the very biggest nearest stars. Those are still very hard to do. But what I wanted to say was that as the telescope diameter increases, our ability to see sizes of things increases. So this is one of the reasons why we want bigger telescopes, is because our ability to see fine structure depends on the size of the telescope. The bigger it is, the finer the structure you can see. Okay, so that doesn't really apply to stars, but for other objects it does. So a telescope that's 30 meters can see structure that's 10 times smaller than a 3-meter telescope because it's 10 times larger. Okay. All right, so the colors of the stars are related to the temperature of the star. And we all know that because our faucets in our bathtub are color-coded. Hot, blue, and cold is red. Everybody's faucets are like that, right? When we look at a blue star, it's a star that's hot. And it's many times hotter than the star that's red. And our sun is on the cooler end, but temperature-wise. So we are, I guess we're not quite red, but we're cooler. You can go a step further than that. And so if you take the light from a star and you spread it out in the spectrum, form a rainbow of the light, and you say, okay, how much is there in the blue, how much is there in the green, how much is in the yellow, how much is in the red, that's a spectrum. And they did this 100 years ago, and Anne Jump-Cannon was the person who understood, and she took all the spectra of lots of stars, and she understood that there was a sequence. There's some stars that are common, and she grouped those into different categories, and she realized that there was an ordering to them, and that these little black lines in them signify different types of chemicals that are in the atmosphere of the star. So these big ones off to the side are hydrogen, and you can, from that, deduce what kind of chemicals are in the atmosphere of the star. So she discovered that in the early 1900s. You can go even a step further, that sequence, this ordering of the colors and the rainbows that she determined, is related to the mass and temperature of the star. Okay, so now we have chemical composition in the atmosphere, we've got the mass, we know the approximate distances, we know the approximate colors, we have a whole census of stars around us, okay, just by looking at the light. Now there's another thing that's really cool that you can do, is that the spectrum that we get depends on the velocity of the star with respect to us. So we can, the velocity speed along the line of sight towards us or away from us. And the lines in the spectrum, where they are in that rainbow, depends on the velocity of that object towards us or away from us. This is called the Doppler effect, and it's illustrated here. So we are that green dot on the left, and we have a picture, kind of a schematic of two stars orbiting about each other. And their spectrums are shown at the bottom, overlaid on top of each other. And the spectrum of A, which is the big blue object in the middle, when it's going away from us, the lines shift one way towards the red, and when that blue object is coming towards us, the lines in the object red shifts to the blue. And it's very similar to when an ambulance drives by you, the sound of the siren changes pitch as it passes by you. Okay? It's exactly the same effect, but for light. Now, this gives us the velocity or the speed of the object with respect to us along the line of sight. You can also get it perpendicular to our line of sight, so in the plane of the sky. Stars move across the sky every night. They're not ones moving because the Earth is turning, of course, so it's just our view of the sky. But in fact, stars do move on the planet time, and they move in the galaxy. And if you wait long enough, you take many pictures and compare the picture to what it was 100 years ago or 10 years ago, you can see small motion. So that motion on the sky and in the line of sight gives you the full velocity of the object. Okay, so now we have the distribution of stars, their colors, their masses, their compositions, and which way they're going. And so we can see flows of types of galaxies, types of stars that move together and other stars that move separately. Okay? Now, not all things have to emit light to give us interesting physics. So what can we infer about the girl in orange, wearing the orange dress? Well, she's spinning around the carousel so fast that she lifts up off the ground. Right? So we can tell how fast she's going around. What's another thing we can infer? There's something holding her on the carousel, right? So she's going around so fast that if she lets go, she's going to fly out. So we can infer by this motion that there's some force holding her onto the carousel. What is it? It's just her arms, right? But imagine that we didn't see her arms. We just saw her orange dress. We could still infer something, but because of the fact that it's going on, she's going on so fast, and she's not flying off, that there must be some force holding her to the carousel. Now in astronomy, we do the same thing just by looking at the light again. We're taking spectra and seeing how the spectra shift, and we're doing a survey of stars across a galaxy. So now in the lower left is a picture of a galaxy, just schematically. It's got lots of stars in it, it's got lots of gas, and this was something that was done by Vera Rubin in the 1960s. She went out and took spectra of the stars in these galaxies and the gas in the galaxies, and asked the question, how fast are they going around that galaxy? And she got an answer. She also said, well, how many stars are there? And remember, we can see the stars, and we say, okay, what is the approximate mass of that star? We can add up all that brightness and get an estimate for how much mass there is. And what she discovered was there's not enough mass to hold all those stars together. They should be flying off the carousel. And so this was really the first good evidence of something that's called dark matter. If there's matter there that creates a gravitational pull that holds the stars and the gas in the galaxy, but we just don't see it, it doesn't emit light, so it's dark. And that was done in the 60s. This was actually, dark matter, by the way, this is sort of another side, but it probably drives the formation of structure in the universe. In the universe, after the Big Bang, when it started expanding, all the structure that formed is probably due to dark matter. There's more dark matter in the universe than there are baryons. Baryons are the stuff we're made of, the Earth's made out of, the planets are made of, the stars are made of. There's something else out there that's there's much more of that, and that determines the structure of the galaxy, I mean the universe. And we're just trying to figure out what that is still. But this idea of dark matter was actually proposed by Fritz Zwicky in the 1930s, but everyone thought he was kind of crazy. I wasn't sure I should put this picture up, because Fritz Zwicky was a really brilliant astronomer who was way ahead of his time. Everybody shows this picture, which he looks crazy on, but he was a genius. Okay, so let's get on to the meat of this. I want you to have a context of why light is so important to us and what we can do with it. And now let's go into the idea of understanding how does the sight affect any of this? How does it affect how we make that measure?
Good question.
Yeah.
About how many of those photons do you have to catch before you can say something about it?
We catch a lot.
Okay.
It depends on the object we're looking at, but it can be millions. But in some of the work we do, the objects are so far away that we're collecting a few hundred, few thousand photons over the course of a few hours. So in those cases, the bigger the telescope you've got, the more photons you collect. So objects are very faint, very far away. You need big telescopes just to be able to see them. It's like when if a storyteller is telling you a story, and you're in the subway, there's a lot of noise around you. You can't understand what's going on. Bigger telescope or better sight reduces the noise. You've got to choose a good sight that doesn't have a lot of background, because you're not going to. Okay. Question?
Could you just repeat the question?
Sorry, the question was. What's the question? The question was, how many photons do we typically collect when we make these observations? And it can be a very small number. And that's why we need big telescopes and good sight. That's one good reason. Okay, so this is a picture of two neutron stars merging. It's an artist's conception. It's not a real picture. And it's made by Karen Murray at IFA. When we look at two neutron stars merging, why do we not see something like this?
Because of gravity. It's very intense around this.
Very intense gravity around it.
Light can't escape.
Light can't escape. Well, in fact, a lot of there's not a lot of light in it, but most of the information is in the perturbations in the gravitational field, which we see in the gravitational wave detectors, this is a depiction of, so it wasn't a very good choice of my object. What else? What's another reason why we wouldn't see this when we look through the telescope?
What is the time space that Merge.
The actual part where all the gravity waves come from is very, very fast, but it takes many years for them to progress.
So the collapse is actually.
It's very quick, yeah.
Looks like the light is directional, so.
So it could be that the light's directional, might not be pointed at us. This object is actually very, very far away, so it's very, very small as well. It's as small as a star, smaller than a star. But we don't have the ability to resolve it. What else might be there? So it's just not primary. Anything else?
Well, knowing where to look.
You have to know where to look. That's
So dark.
These things are rare, so you have to know where to look. But even if we could anticipate that where they were, we wouldn't be able to see it because they're just too far away. They're too small. So we don't have the resolution to see them. Okay, so let's get into some of the things that make that limit our ability to see these things. So the last slide was really just to tell you that when we look at these things, there are lots of things that will prevent us from seeing them. Some of them are physical; they're just too far away. But some of them are our choice of where we telescope. Okay? So let's go into some of the big reasons why what makes a site good. So when we speak of a site for a telescope, we think of it's got to be a clear site. And to an astronomer, clear means a bunch of different things. So the first thing, this is a picture of Maunakea, and I believe that's maybe the satellite road, or maybe possibly from the road to Mauna Loa.
From the observatory.
From the Mauna Loa Observatory. Yeah. You took that. I didn't give you credit, sorry. Peter Michaud. So what do you notice about this image? How is it clear? That's Maunakea, the telescope are on the top. The sky's clear. There are no clouds up there. So first thing is you want to have a clear shot to see the stars. You don't want to cloud above. And the principal reason why the clouds on the Big Island are kept below the summit level is because of the inversion. The inversion layers, so normally when you go up in altitude, the temperature drops. But there's a location, it's called the inversion layer, where as you go up, the temperature actually increases. The very thin layer is about 1 kilometer thick, maybe a few hundred meters thick. And then after that, it continues to drop as you go up. That change in the gradient of temperature creates a kind of a zone that clouds don't want to propagate up through. So it keeps stuff down. And the inversion layer is generally below the summit. During the day, sometimes it weakens, so clouds come up. But at night, it almost always forms, and it keeps the clouds down around the peak of the satellite where it's low. That's extremely important for Maunakea. It's actually caused by the fact that there's this high pressure system that's typically just to the north of the islands. And this high pressure system is caused by the inversion layer. It's the thing that gives us the trade winds. And basically what happens is, here's a schematic, and this schematic is a slide from Fritz Glasner. Thank you, Fritz. This is the Earth's, a graphic of the Earth, and the North Pole's at the top, South Pole's at the bottom, and flow in the atmosphere of the Earth is in cells. So the flow of the atmosphere near the equator is rising. Okay? That's denoted by these arrows kind of on the left. Right here. So this is the equator, and flow is upward here in the equator. So there's kind of a cell of motion of the air. And near the equator in the Tropic of Cancer, this thing is the thing called the Hadley cell. And this is true all around the Earth. And what's nice about this is that up where we are, here's us, just below the Tropic of Cancer, the flow is downward. That's what causes the high pressure system. And that keeps moisture down by the equator away from us. So the flow is on the surface is down towards the equator. If the flow were upward to the north, it would suck moisture up from the equator towards the Hawai'i Islands. So normally, this high pressure system is there because this flow is here. And that gives us a sky that's very clear. So this is a picture of the night sky. just looking up, it's a wide field lens, it's on a camera, and you just take pictures and you can see all these stars. This is the Milky Way, and there aren't a lot of clouds there. That's the kind of night sky you want to have. Not only is it clear, you can see that there are clouds, but notice that there aren't variations across the sky. Part of the job of making a measurement is to understand what the story is in quantitative. So we need to calibrate all of our data, compare it to known standards, stars and known brightnesses. And that means that variations across the sky have to be small. And so when you have a clear night like this is what you get. Okay, I have to say that this is actually what it looks like today. This is a satellite image. We are right here. That's the big island. And this is like the equator. And we have no high pressure near us. And so the flow from sorry, this is very fast. This is not real time. But these green and red things are clouds, high altitude clouds. The red things are really tall clouds, storm clouds. And they're being sucked up from the equator towards us. And that's what's giving us our crappy weather in the north. And if any of you went to Ryan Lyman's talk, which was last month, on meteorology, I remember in the audience, I was sitting there and I was thinking, oh, I have to give this talk in a month, about 5 months, yeah, so good. And he showed these plots a month ago. And it hasn't changed, unfortunately. We've had a really bad spell of weather. So I was kind of hoping it would be all the bad weather would be taken up by his talk, but he was refused to change the forecast for the mountain. And that's what it resolved. But okay, I just wanted to show you that's not always good. So one thing is cloud cover. You need a clear sky, a clear shot of the sky. But clear means something else for astronomers as well. So does anyone know what this is a picture of? This is the moon. Right here is the moon. So what else? It's an eclipse. It's a total eclipse. So the moon has passed in front of our line of sight to the sun. So this thing in the background that's being blocked by the moon is the sun. The sun's right behind it. It's quite fortuitous where we live that the angular size of the moon and the angular size of the sun are not the same, and that every once in a while the moon passes the sun. And that's where it goes. It's a spectacular sight. So if you get a chance to see it, it's really beautiful. So people knew that when the moon passed in front of the sun, that they could go out and look for features around the sun, faint features on the sun. And this is a picture of what you see. You see particles that are streaming out from the sun, electrons or protons. And these things emit light. And you see these filaments and streams of stuff. You can't see them. They're usually there, but you can't see them just because they're too faint and the sun is so bright. Okay, so oftentimes we're looking for faint things by bright things. And so that brings us to this idea of what does clear mean? Well, sometimes you have particles in the upper atmosphere, aerosols, dust, grains of salt. And what they do is they don't block the light completely, but any light that hits them scatters and changes directions. So it's like holding little mirrors up in the atmosphere. When light hits it, it just changes direction, but it keeps going. Okay? So this is an illustration of that effect. You go and take the angular size of the sun is about the size of your pinky fingernail at arm's length. The sun is not that small, but angularly it is. So you should be able to hold up your arm, never look at the sun too. Okay? But if you were to look at the sun with your finger blocking it, your pinky would cover it. Okay? But at sea level, this is kind of what you see. That's not your finger, that's somebody else's finger. But you see a glow around it. It's because sunlight is being scattered in the atmosphere of the Earth. And it's coming from, it appears to come from other directions. So you see the glow around your finger. As you go up in altitude, the amount of aerosols in the atmosphere drops very quickly. And so as you go higher and higher, that glow around it gets smaller and smaller. So if you were to go to the summit and do this, when you faint, you would see nothing. And so this kind of glow adds to the background, adds to the noise. It's like people are talking, you can't hear the storyteller. And so it's hard to detect something that's faint by a bright thing when there's all this happening. Okay? So the amount of aerosols that are in the Earth's atmosphere depends on where you are, continental geosites, urban areas, big cities off, there's pollution, there's soot in the air, that scatters a lot of light. The best sites are ocean sites around where those the subtropic high is, so around Hawaii. There's one site that's better, so that's one factor of 1,000 better than there's one site that's about a factor of 10 better than us, and that's the South Pole. Not the North Pole, but the South Pole. I'm not quite sure why the North Pole isn't good, but the South Pole is even better.
Altitude.
Altitude does make a difference, so the density of the stuff drops off very quickly, as does the inversion layer. So what things can work against us? There's lots of things that can work against us. This is an illustration. I don't want to pick on the Canary Islands, but I'm going to pick on the Canary Islands. So this is the Canary Islands. This is the west coast of Africa. The Canary Islands are right here. And what is it? This is a satellite image, of course. What is it that we see? We see sand. So sand from the Sahara blows out into the ocean, and it adds to its particulate. Not to mention that it's really bad for all muscles that are blowing sand on things. I don't know if you guys are paint things or rust on things. You get a sandblaster, and you can take stuff off. This is not good. But anyways, okay. Canary Island. So that's particulates in the air. But again, there's lots of things that contribute to this. So, fog is bad. Volcanic ash is bad. So we're lucky we have trade winds, that they blow in the other direction, and we're lucky we have the inversion layer. So if those things were to go away, that would be bad. Okay, I finish at 8. Okay, thank you. All right, so clear means other things. So it means we have clouds above us. We have a lot of things scattering the light. It also means that what we see is not heavily affected, in the sense that in this picture, this is like this is up on Maunakea someplace. I don't remember where it was. But basically, you're sitting in a cloud, so you can't see. Depends on wavelengths, though. The color of the light. For example, if you're in a car driving over a satellite road, it slows the radio, right? Even if you're driving through a cloud. So some wavelengths get through different things. So it depends on wavelength. And here's a very graphic display of that effect. So what I'm plotting here is, this is transmission. So zero transmission means that you have completely blocked your view. A transmission of 1 means it's completely clear. And this is a function of wavelength. And these are very long wavelengths. Visible light is kind of half a micron. These are much, much brighter than that, but I picked this particular region because this is very sensitive to water vapor above the site. So water vapor acts like a cloud to these wavelengths. And it's very selective in wavelengths, so the color. And so all these kind of lines for us change our ability to measure light at these wavelengths. Okay? So for example, at this wavelength, just shortward of 24 microns, we can't see it all. The Earth's atmosphere completely blocks our view. But just longward of it, there's a little window where we have some transmission. You can see light coming down. But how much water there is above us changes this dramatically. And so I want to look at a photon that's carrying some important bit of information and happens to have this color. It happens to be this wavelength. I need a site that doesn't have a lot of water above us in order to make that observation. And in fact, at these wavelengths, there's pretty much only 2 sites in the world where you can do this from the ground. And Maunakea is one, because we're high enough that you don't have a lot of water vapor above us. The best site for this is Antarctica. Why? All the water is frozen out. There's nothing in the atmosphere. So it's a very good site for infrared observations. Okay, so to me, clear means yet another thing. When you look up the Earth's atmosphere at a star, every child knows a song. What is it that happens to the star? Twinkle, twinkle, little star. Its intensity fluctuates. Brightness fluctuates because it's passing through the Earth's atmosphere. So complete artifact of the fact that we're looking through the Earth's atmosphere. And there's nothing intrinsic about the star. The starlight is just going through the Earth's atmosphere and it's getting blurred out. Sometimes it appears brighter, sometimes it appears fainter. And this is a movie of what a star looks like on a big telescope. If you were to put your eye at the pole from the telescope. Now we don't normally do this. We normally have a camera that looks up and records the image for us. That's how we got this image. But if you were to put your eye there, this is what you'd see for a star, which you can't resolve. It should just be a little point. What you see is a big blob of stuff dancing around, moving all over the place. That's due entirely to the Earth's atmosphere. And we call this, we refer to this as seeing. I have no idea where that, I guess it's our ability to see. I don't know where that comes from. But that's what it is, and that ruins our ability to resolve fine structure. Remember I told you that a telescope that's 10 times larger than another telescope has the ability to resolve things 10 times finer? Well, now we have the Earth's atmosphere. So the Earth's atmosphere blurs things down. And so the big telescopes don't have the resolving power that they should have because of the Earth's atmosphere. In fact, the resolving power of the telescope is no greater than a telescope about this big because of the Earth's atmosphere. Okay? That sounds awful. Why is that really important? So here's my example of why resolution is important. This is Galileo. Does Galileo have a last name? Galileo. I always thought it was like Madonna. They only had one name or something. Galileo was one of the first people to use a telescope to look at astronomical objects. And this is the this is the first object, one of the first objects we looked at. And what do you see? I see a big blob here, and another blob here, and another blob here. That's what Galileo said. So he said, aha, that's clearly 3 spheres. Big one and two next to it. But the object he was looking at was that object. He just didn't have the resolution, in part because the site he was at wasn't good, but also in part because but resolution can lead you astray. So you can misinterpret. Even the best of us can misinterpret because we don't have the resolution. So that's resolution. Resolution is also that car headlights experiment we talked about before. Car headlight coming at you can't resolve the headlights. It's just a resolution problem. And astronomers typically talk about something called the unit they use is 1 second of arc. So there are 360 degrees in a circle, 60 arc minutes in a degree, 60 arc minute. I lost track. It's a very small number. If I pull my hair out on my head, it's about 100 micron thickness. It's amazing. If I hold it at arm's length, that's 20 arc seconds. I gotta hold it up 20 arm lengths. So if Fritz was holding my hair, that angle is dependent by the thickness of that hair as 1 arc second. It's really tiny. So telescope sites are really good. They have a lot of resolution. But nonetheless, the resolution should be driven by the diameter of the telescope. The bigger it is, the finer it can resolve. Right? And we're not achieving that. So you want to go to a site that has a good resolution. Right? Okay, so if we were to take our telescopes and point them at the horizon or Honolulu, we don't do this. You can't even see it anyways because of the curvature. Normally, we don't want to point our telescopes this low. If you were to point it at Honolulu, 1 arc second splits can resolve the headlights of the car in Honolulu. Okay, so that's pretty good. Now, the first person to understand turbulence in the Earth's atmosphere that causes steam was Van Gogh. And this is 1889. And I don't know what he was doing, but he got it really good. Because this picture is the picture I show at every talk I see it. The researchers doing this level forever. And what it shows is that in the Earth's atmosphere, there's all this stuff moving around. And here's the hillside, and just above the hillside, there's this layer. That's the flow. That's through the flow of the wind over the surface. Topography. That's called the ground layer. And then in the upper atmosphere, we refer to it as the free atmosphere. There's still stuff going around. It's heated by the sun during the day. That's the thermal energy. There's wind up there. There's jet streams. That's the mechanical energy. So those two combine together give you the turbulence and seeing things. Okay, so why is Maunakea so good? This is a slide I stole from Gunter Hassinger. One of the reasons is because we sit in the middle of the ocean. Flow over the ocean is very smooth. And then basically a little pimple appears and the wind just kind of blows like line around. Very smooth. So what it gives us is a very weak turbulence in the boundary layer and the atmosphere. And that's a characteristic of Maunakea that we've known forever. When they first did the tests, they were astounded and they realized this was a really good site. Over the years, we've gotten better ways to measure it, but the answer really hasn't changed that much. I'm going to throw a slide at you. It has numbers on it. I apologize. When we go out and we measure how much seeing there is in the upper atmosphere, not near the ground, just the stuff above this ground layer, we see that it's absolutely exceptional. So a typical site in continental US is 1 arcsecond seeing. Maunakea is about half an arcsecond or so. And when you get above that boundary layer, the surface layer, it's even better, it's a third of an arcsecond. There's no other site better than this, except for maybe Antarctica. And Antarctica's boundary layer is about 150 meters thick. So you've got to put your telescope 150 meters up. Okay. All right, so I don't remember why I put this on. So we're just going to keep going. In the interest of, okay, right, okay. So what do we do about this? Seeing is absolutely a horrible thing. Why would we ever put a telescope on the ground? Well, there's a technique called adaptive optics, which allows us to take the recording effect out. And so basically what it is that we sense what the distortions are in real time. These things are constantly changing. You saw in a movie that's constantly changing and moving around. You can look at images like that, figure out what's going on, and correct it. 1,000 times a second, we update this mirror in our system, and it takes out the blurring. That's called adaptive optics. I'm not going to go into detail on that. That's a separate talk. But here's a little animation that shows you how it works, or shows you it working. So we'll wait till it starts over again. That's the answer. Okay, so here's where, just similar to that image I showed you before, there's lots of turbulence, things dancing around, blurry. We turn the adaptive optics system on, you get this nice bright core with a ring around it. That's theoretically what you get when you have a circular aperture telescope. That's an adaptive optics system working. And with that, the telescopes, now the resolution is set by the diameter of the telescope. The bigger they are, the finer the detail we get. And so now, if we put adaptive optics systems on the big telescopes on Maunakea, like the Keck telescope, we can get a resolution that's 20 times better, and we can now resolve the headlights in Colorado. I mean, I keep going back to the headlights, but we never look at headlights. It's just an example. All right, so that to me is one of the things that makes a site clear. There's another thing that I would consider under the category of clear, and that is the darkness of the sky. So there's lots of ways to make a sky not dark. If you're by Honolulu, it's hard to see the stars at night. There's all these city lights. So a dark site can't be too close to a city because there's light pollution. Now, if you notice that when you drive around Big Island at night, it's very dark because there's a county ordinance to protect how much light is projected on the street. Now, the lights that we have on the street, we need to light the streets so we can see. But I don't know if you remember, but it used to be that the street lights would be pointing in all directions, kind of willy-nilly. And those sometimes are going up, they're just scattering the sky fire. They're not lighting up the street below us. So that's what the improvements have been over the years. So here's another slide from the grid. This is a comparison of polymer at the top. That's the 200-inch thing, and Maunakea. And so these are on the same scale as a log scale, but I think you can see the point right away. And when you take a picture of the sky on polymer, which is a sort of incredibly important observatory in Southern California, you don't see astronomical objects, right? Because it's so bright. But when you do the same kind of thing in Maunakea, you see this is the Milky Way. The things that you see that are bright are astronomical objects. That's what you want. But a sharp eye will see that along the horizon there are these other things. So we have to be careful. We have a very dark site on Maunakea, but we can do bad things to it. So this is a picture from Richard Wayne's kind of thing. And this is basically, sorry, the resolution is very good, but this is looking up from the mountain towards Honolulu, and you can see the glow of the street lights in Honolulu. And that has an effect. Also the resorts are very close to us, so they're bright as well. The worst offender seems to be the rental car lot at I think in Hilo, it's got to be the UH Hilo baseball field, which seems to point its light straight up. I don't know. But anyways, the important thing here is that you have to keep the sky dark, and it's really easy to ruin it. Those zombie headlights, you guys know what I'm talking about? I keep going back to the car headlights. This should be a subtitle of car headlights, but the zombie headlights, when you're driving, they kind of blind you because they're really bright blue. Those are really awful, not just for us to be able to drive, but that blue light scatters a lot. So the atmosphere will scatter light more in the blue than it does in the red. So when we project blue light up in the Earth's atmosphere, it's really bad for astronomy. And Maunakea historically has been a very dark site for being able to work at short wavelengths. And that's a very important wavelength because there's a lot of physics that emits photons at that wavelength. Okay. All right. So darkness also depends on natural things. The moon, when it comes up, those are when the full moon is up and we're observing. That's called bright time. Because there's nothing we can do about it. We can observe at wavelengths that don't matter. So we observe at redder wavelengths. When the moon's down, it's very dark, and we'll work at the bluer wavelengths. So as long as we preserve the dark sky for that. Sometimes, and I'm going to go back to the South Pole. This is a picture taken at the South Pole over the course of the day. Or sorry, over the course of the month. No, sorry, it's a day. This is the moon. So the South Pole is interesting because during summer, the sun's always up above the horizon. It's always daytime. In the winter, the sun's always down below. So you have really long nights. So that sounds good for astronomy. The problem is that the moon also comes up. And it basically skirts along above the horizon. So you never have dark time. You always have light time. Does it mean something? And if you count the number of dark nights that you can get at a site like the South Pole versus the number of dark nights you can get at a place like Maunakea, Maunakea is significantly higher for the dark time. So that's the quality time you want for working at short wavelengths. Okay, so why, with all these things that work against us, why would we ever want to put a telescope on Earth? Well, cost. To launch a telescope into space is incredibly expensive. Many billions of dollars for the space telescope. The size of the telescope, you can't launch something that's that big. You can't launch a 30-meter telescope. The next space telescope to launch would be the James Webb Space Telescope, which is a 6.5 meter. And that will be a technical. I'm sure. Yep.
Given that the space telescopes are above the atmosphere, what's the equivalent of a 30-meter telescope on the ground? The other outside the atmosphere, with 6 or 8 meters, capture 30 meters on the ground.
So let me see if I can paraphrase your question. If you could launch a big telescope into space, what would be the equivalent of 30-meter telescope? When you're talking about space, you don't have these problems with atmospheric blurring, you don't have these transmission windows you could deal with. But the telescope's smaller. So remember, the resolution and ability to resolve fine objects depends on the size of the telescope. So if you have a 6-meter telescope or a 10-meter telescope in space, you still can't resolve as well as you can with a 30-meter telescope because the aperture's not big enough. So for some things, you do much better. There's no sky background, the infrared background is very low. You can have more sensitivity. But for some other reasons, you just don't have resolution power. And you don't have the collecting area to see faint things. Things that are faint down on Earth, but still faint up in space. So you need collecting area. So there's kind of for some wavelengths, you have to go to space, and that makes sense. For some other wavelengths, you don't have to go to space. And because of the cost of something in space, it just doesn't make sense to do that. So they're complementary in that sense. A ground-based telescope is flexible. The lifetime of a ground-based telescope is about 50 years or so. You can go out to new instruments, you can update it. The space telescope that you launch far away from it, you one shot. And in fact, the technology that's in the space telescope that they will launch is actually quite old on the ground past that. So, but they can't, because they have to launch it, they have to track it and get it ready to launch into space, and they can't do that. So access, and by access, I don't just mean that you can go and fix it, but I also mean you can train the next generation of scientists on these telescopes, because they can touch on it and understand how it works. I think it's a big thing. And then serendipity and experimentation. You just can't experiment on a project that you're going to launch into space. It's got to work. It's got to do the piece of it. It's too expensive to experiment. So I think let's I'll quickly go through just a few more slides, but astronomers have tested many sites. So they look at these parameters and they have instruments that measure all these things. And they deploy them at different sites around the world. And they try to compare and see what sites are best. And these are some of the sites that people have tested. And in all the things we've talked about, all of them. One makes it clear. TMT did a very nice job. They deployed a whole suite of instruments, all identical. They set them up at one site, tested them so they gave the same answer, and they deployed them to 5 different sites. They did a big campaign over multiple years. In fact, the 5 sites were Hawaii, San Pedro Martir, which is in Baja California, and then 3 sites in northern Chile. Almost all these sites have telescopes already, or telescopes near them, so you're comfortable with them. There's one site, this one was at fairly high altitudes in northern Chile that there was nothing at. They knew they wanted to have a high site, for some of the reasons we talked about. So they stuck that in. Just a note that the site they tested for TMT, this 13 North site, is not on the summit ridge. So this is a satellite, this is an image taken from space. This is what we call the East Ridge, and this is what we call the West Ridge. That's kind of at the summit. The true summit of the mountain is over here, I think. But the site they tested for TMT is called 13 North. That's below the summit to the northwest. Okay, so it's below the summit. And although we never did tests at the summit and at 13 North at the same time, I think there's strong evidence that says that the summit is better than 13 North in many respects, especially in terms of the seeing. But TMT went and they measured all this, just to impress you with all the things that they measured. They measured a lot of different parameters. But in the end, the consideration was really that collectively, Maunakea is the one that is the best in terms of if you want to work at all these different wavelengths, what do you need? You need all these things to be good. And collectively, you only find that really in Maunakea. So I'm going to quickly go on to just a few examples of science that we've done on the mountain, not me, but astronomers have done, that were really enabled by something special about the mountain. There are many things we can offer that. I just picked the ones that, to me, I don't know, get me excited. So the first one is this image. This is an image taken by the UCLA Galactic Center group, and it's demonstrating what happens when adaptive optics is turned on. So this is adaptive optics off, so we're just limited by the natural seeing of the site. This is probably on the Keck telescope. When we turn adaptive optics systems on, you can see much finer detail. You can resolve the objects. And the group, led by Andrea Getz, over many years, almost 2 decades, have looked at the Galactic Center, and they said, well, let's just look and see what the stars are, and see what their motions are. And this is, it's a plot of what the orbits look like. Sorry. And so over the number of years, they've taken many images. And remember, it starts in 1990-something, and it'll go all the way through to 2017. And what you see is that these tracks follow where they saw stars moving. And just like Vera Rubin could infer missing mass, they've determined that there's an object at that location that has 4 million times the mass of our sun, but emits no light. So that's the central black hole of our Milky Way galaxy. So we've measured the mass of it. What's also cool about this is that this is the track, the orbit track of an object called SO2. I have no idea where the name got from, their names. But what's cool about it is that notice it's right here, 2017.7, so just at the end of last summer. This is where it was. And this year is going to be passing on its closest approach to the black. What's cool about that is that general relativity, Einstein's theory, says that if there's a supermassive thing right here, this orbit will precess change a little bit. So as they go on, they will see this orbit through those, right? They'll see that oval changed orientation. And that's a test of general relativity. So there's lots of tests about general relativity, but this is the one that will happen next year and the following years on Maunakea, which is really cool. Okay, so let's keep going. And that's done with adaptive optics. This is another observation with adaptive optics. And this is totally random. This is a picture. This is one of the first images of a solar system around a different star. So, what year was this? 2004? So with adaptive optic systems, because you get a clear view in these big telescopes, you can resolve these planets around those stars. This picture's a little bit weird. Okay, so these three spots are planets that orbit around a star that's right here. The star is so bright that we've blocked it out. We've just taken it, and there's techniques to block that star. Similar to like holding your finger up from the sun. So this needed adaptive optics, and it needed like, clear stuff. And so since then, what they do is they take many pictures again, and they see those things moving around the central star. And that tells them, yes, in fact, they are gravitationally bound. And since then, there have been more systems discovered. These streams are leftover stars that were ripped apart from the whole galaxy. And we think that this happens to every big galaxy. And when we go up, and in fact, there's the Pan-STARRS project, which is on they've been looking at the stars around our galaxy. We see similar streams around our galaxy. This is giving us a clue about how big galaxies form. They're gobbling up smaller galaxies moving bigger and bigger. And this galaxy will eventually fall in as well. So I just think that's a really cool picture. So I want to mention one last thing. When you look at the seeing turbulence above Maunakea, where I told you the reacts are very deep. Self-magnetic ground on Maunakea seems to be very confined to within a few hundred meters of the telescopes. Imagine this photon traveling to you for 1 million years. In the last 100 nanoseconds of light, 10th of a millionth of a second, it travels through this last bit of atmosphere, and we've told this stuff 2/3, maybe half, of this turbulence arises within 100 years. It's worse at the 13-yard cycle TNT is. This is the profile of the seeing that you would get if you put the telescope higher and higher. And so if you were to get up to 100 meters, you would have 30 times. I told you that 3 atmosphere seeing on Maunakea is excellent. It's 3 times better than any other place to go south. And you have to try to get the telescope 100 meters up. Now that's impossible. You're not going to build a tower that's 100 meters up. But there's a technique called that optics. And we're developing, trying to build these wide field of view that just correct for this layer for a telescope like TNT. And if we do that, it effectively turns this telescope into a more sensitive machine instead of a 30-meter telescope. Which incidentally is no coincidence because the Europeans are building a 39-meter telescope in Chile because Chile is not as good as Cyprus. And so if we put this on TNT, I'm going to get we do as good as them in terms of sensitivity, we can resolve that by expression. So that's my just that stuff I work on, so I just want to throw it in. So I'll conclude here and just say that it's really that combination of many things that work many different wavelengths, from the bluest wavelengths all the way up to the mid redder than our eye can see, that these qualities at the site make it unique. There's no other site that collectively can do all of it.
Given the plan B for the 30 meters Canary Islands.
Yeah.
You showed us it's an over elevation issues. Maunakea is 10. What would be great is the Canary Island size.
That's a good question. Okay, so let me paraphrase the question. What would happen if TNT went to Canary Islands? I'm not going to read it. It's extremely difficult, actually, to compare two different sites when two different groups do the measurements. And no measurements have been done between Maunakea and Canary Islands. So this is why the TNT group did a really good job. They took the same equipment, set it up, compared it, and they took the different sites. So that, I think, is a fair comparison. Maybe the absolute numbers aren't right, but the inter-comparison is fair. But we've never done that between the Canary Islands. One thing is for sure that it's a lower site, so the water vapor will be higher. They're not going to do it in the rain. They're just not going to do it. So we just get rid of that. The seeing, I don't know how good the seeing is. So everybody over the last 15 years has tried to say that there's good Maunakea in terms of seeing. And every time I go to a conference, I'm going to stand up and say, see, Mark, where's good Maunakea? So, well, that's one primary measure. There's 10 others, but I don't say that.
Can you make more comparative comments about the Chile site?
Chile is an excellent site. Number of clear nights is higher in Chile, upper 80%, 87% or higher. Number of clear nights, no clouds. Maunakea is more like 76. But when you, the TNT group tried to take all this into consideration, they had a dozen parameters, and they tried to come up with an equation that said, oh, this is the type of science we want to do, and this is how much science we can get out, given these conditions. And they selected Maunakea. But northern Chile is an excellent site, very clear. The seeing is far less good. They don't have something like this ground there, very weak upper atmosphere. But it's very sense.
The Chile site is right, you have mixing because of the mountains, so you have to phase the wind. So
There's an interesting story about when they built the very large telescope facility, ESO's BLT. They did a lot of site characterization before, and they selected the site as a very good site. It's still a great site. They built a mountain, and the conditions on the mountain changed a little bit. The wind direction changed, so the seeing changed a little bit. That's still what you do to the mountain.
There's obviously opposition to it in Maunakea, and I understand from recent publications there's opposition to it also in the Canary Islands side. Is there any opposition to citing such a large facility in Chile?
There have been issues in the past. My general impression is that the Chilean government is interested in bringing facilities to Chile. That's a general comment, based on the last 20 years. We can now have a collection of many large telescopes, so they may be less inclined to bring more telescopes in, but they have certainly a large collection of really good telescopes. So this is kind of a personal experience. But I've worked with many Chilean astronomers and engineers. And one difference that I see when I went to observe in Chile is that the Chilean workers at the observatories really consider the telescope there as their national observatory. They're very proud of that facility. I think that's something that we haven't done a good job at here, is having this be
Just to follow up too, are you aware of what the extent of the opposition is in the Canary Islands site compared to what the opposition is Maunakea?
I can say it.
Okay.
Does it make a difference which hemisphere you're into because of what you can see?
That's an excellent question. So the question is, does it matter if you're in the northern hemisphere or the southern hemisphere? You see different things depending on where you are. In the northern hemisphere, you see things like the Andromeda galaxy, there's a big galaxy. In the southern hemisphere, you see things like the large amount of clouds. These are the largest satellite galaxies going around the Milky Way. You see different things. So ideally, you would have a telescope north and south, which is like the Gemini telescope. Northern facility, southern facility, you see cover the entire sky. But that's not really practical in one institution to do. So the hope is that with something called south, north, and those communities.
You were mentioning the idea of having Gemini north and Gemini south. And is there an advantage to having the exact same piece of equipment in both sections rather than having a large telescope in the north and another different large telescope in the south and then trying to compare?
I think in principle that sharing of identical facilities is a good idea. I think it's difficult in practice to keep them identical when you have different groups working on them. And their missions might be different. So in the early days of Gemini, because Maunakea is so good in infrared for adaptive optics, we decided that the northern telescope would be the adaptive optics telescope. In reality, it turned out more to be the opposite way, with more adaptive optics coming on the south, but here. Did you have a question here?
Have your meteorologists modeled any of the possible impacts of climate change on your side? Because obviously viewing time is related to where the critical inversion is, which is a function of the cooling of the atmosphere. Of course, one of our most famous observatories is on Maunakea, where energy CO2 is the atmosphere.
Right.
Would any of these sites, some places in the world, where climate is changing more rapidly than others? This could have an effect on moving time and parameters, correct?
I think that there could definitely be an effect. I don't know of a specific study for Maunakea that's been done. I think that same question was asked for Ryan a month ago, but I don't have an expertise to say. It's a complex calculation. It's very important. The version layer and the that point.
So I'm going to jump in here and address Dr. Juvic's question and encourage him to come to other speaker series sessions because Dr. Businger from University of Hawaii actually has been doing the climate change downscaling study. And he's got a paper that's been submitted for publication on this very subject. I'm not going to try and paraphrase it to probably get some of the technical aspects of it wrong. But yeah, there has been some work on climate change. It's not a game changer as I understand it, but it will have some noticeable effects. But thanks for the question, Jim.
Any other questions?
I have one. You mentioned the street lights here on the island. Are you happy with the changes? Some of them are making now. I noticed there's a different type of lights, street lights in the installed.
The county's been pretty good. There's basically one county engineer who's tried to light. So we have a good relationship, convenience relationship. When the LED lights came out, we noticed that the sodium pressure or whatever lamps that we used to have different elements of this with LEDs. When that first was decided, they were going to use an LED similar to these zombie lights. We have an extra component of blue. So we talked to them about that.
I just want to follow up on the light too. I've got to ask you before. We live in a very dark place. At night time, we see very big lights. But then when Kamehameha School Stadium lights come on, and other stadiums don't, I suspect on them, but we overlook them. Does that reach up to where you are for mountain, or there's no effect?
All these lights have an effect, especially on a moonless night when we're working in the bluest that's the New Age baseball field is.
You mentioned that the lights on that one car lot were really bad. Doesn't the county come in and tell them they have to modify, change, or re-engineer their lighting system?
Yes, the question is, hasn't someone gone and told the power rental companies on airports and things like that? I don't know if enforcement is, how enforcement is done, but there are safety issues and traffic issues that they worry about, so I don't know if we can offer it. But again, I shouldn't say I'm not deeply involved in that.
The following that is light oil is only going to grow. It becomes a hotter and hotter light spot. is there, are there building restrictions on light as there are on elevation, height, and everything else?
Not that I know, but there's certain lighting ordinances.
Yeah, one last question, sure.
I was curious if somebody drives a vehicle up the mountain during the night, does the headlights from the vehicle cause problems with the sun?
Yeah, there's a sign that says use your blinkers, your flashlights, your headlights off, because you get those presents on. I remember one time I was working at a job night, it was a meteor shower, and we were seeing all this strange background, and we couldn't understand what it was. And we walked outside, and it was just a parking lot of cars, and they all had their headlights on, and so we had to see that. Okay.
All right. Thanks very much, Mark.